Welcome back to ECE 501B. The next time you are here will be exam number 2. Hopefully that doesn't surprise you. And if you're listening at home, it's whenever you have signed up. Hopefully you have signed up to take exam 2 at the appropriate time. Homework number 6 is due tonight, and that material will obviously be a part of or included on exam number 2. Project, that description and the deliverables, just as a reminder, there's 3 deliverables and they have 2 different sets of due dates. The first one is due before the Thanksgiving break on the 21st of November, and the 2 and 3 deliverables are in a package. Number 3 can really be a page or a paragraph that's appended on to your main project report, which is deliverable number 2, and that's due on the last day of class, which isn't very far away, in fact, relative to the number of classes. We're, I think, over 60% of the way through the semester in terms of times that we meet. Today what I want to do is continue with Chapter 7, but before we do that, let's just make sure we're on the same page, or at least partly on the same page, relative to exam number 2. You can get a glimpse of what to expect by looking at the review material on D2L, and that will then be followed by Chapter 7 material. We'll recap the adjoint map and what it means to be self-adjoint. In parentheses, that's really what it is the linear map is equal to its adjoint. That means you have a self-adjoint operator. We'll look at a simple linear map and find out what that allows us to think about in terms of an adjoint relative to a complex number. So we'll view a map like we might real numbers and complex numbers. Then we'll state some propositions and corollaries for self-adjoint maps. We'll look at normal operators. We're having a lot of operators. We have linear operators, we have adjoint operators, we have self-adjoint operators, we have now normal operators, and what does that mean? And in one way of thinking about a normal operator, you can think of it as combining the linear map with its adjoint, and if it doesn't matter how you order those, which one you perform first and which one you perform second, then that linear map is a normal operator. Meaning the linear map and its adjoint commute. If you're thinking matrices, that's like AB is equal to BA. Here we're dealing with maps, so the linear map applied to its adjoint equals the adjoint applied to the linear map. That's not the same as saying the linear map is equal to its adjoint. But if you do have a self-adjoint operator, remember what operator means. Operator is different from a linear map, or it's, I should say, a more specific linear map. An operator is when we're going from the input vector space and the output vector space are the same. But now, if you have a self-adjoint operator, that automatically is a normal operator. And I've sort of shown in black underneath that statement why that's true. If the linear map is equal to its adjoint, then if you look at the concatenation of the map with its adjoint, you can say, well, that's just the map and the map. But the map, the linear operator, is also its adjoint, and so now you can see that they commute. But you can't go the other way. You can't make the statement that a normal operator implies a self-adjoint operator. So that direction doesn't work. And then we'll look at maybe a reason why we might call these normal operators is because we can show, or that we will state, if it's a normal operator, then the norm of the linear map applied to a vector is the same as the norm of the adjoint of that operator applied to that same vector. That's a definition of a normal operator. All of these then lead to relationships for eigenvalues and eigenvectors of these linear maps and their adjoints. We'll look at normal operators and distinct eigenvalues. What do we know, review, for exam 2 about a linear operator and it having distinct eigenvalues? What do we know about that kind of a relationship? If I give you a linear operator and I say it has distinct eigenvalues, what can you come back and tell me factually about that linear operator? Can you tell me any more information if I tell you, oh, it has distinct eigenvalues? So you have linearly independent eigenvectors. Linearly independent is not the same as orthogonal, is it? And now we can talk about orthogonal since we have inner products. So this is obviously a stronger relationship if we have normal operators, not just linear operators, and the fact that those normal operators have distinct eigenvalues. Then we can say not only are those eigenvectors linearly independent, they're orthogonal. Then we'll get into some spectral theorems. Let's get started with the day. Exam number 2 process, 3 sheets of notes. I think last time you had 2. Now you can add on to that, front and back. 8.5 by 11 are the sizes. If you're wondering what those 2 tick marks mean, those are inches. So it's 8.5 inches by 11 inches, the standard paper dimensions in this country. Calculator, writing instrument, I don't know how much you'll need the calculator, but you'll definitely want to bring something to write with. But what you can't have access to are the textbook, the notes. You already have 6 sides of a paper for your notes, but you can't have anything more than that. No cell phone, no computer, no neighbor, etc. Questions on that should be consistent with exam number 1. Topics, chapter 5 and chapter 6. Eigenvalues and eigenvectors, inner product spaces, so obviously inner products. And it's really more than chapter 5 and 6 because we're climbing up, or we're progressing through this book. So we can't forget chapters 1 through 4 if we're now in chapters 5 and 6. Otherwise, the foundation would be torn out from underneath us, and we couldn't really do much with chapter 5 and 6 necessarily. So if there is material that you need to have available in your noggin or somewhere relative to chapter 5 and 6, you need to keep track of that. And homework 4, 5, and 6 is what we're dealing with material-wise, so you need to be able to apply that theory. I might have you create something or build something based on your understanding of eigenvalues, eigenvectors, inner products, etc. Let's continue then with chapter 7. And I'm going to scroll just for a little bit because this is a review, so we can kind of get through it. But adjoint maps are such that we have this equality relationship with inner products. And inner products can be different for given spaces. And on some of the practice exams, I might have said, is this a valid inner product? And it may not look like the Euclidean inner product or the standard inner product that you're used to thinking about. So you need to get comfortable with these inner products being something other than the Euclidean inner product. And obviously that's true when we had polynomials as our vector space. then we had multiple inner products that we have played with. But if we have an inner product and we want to know what is the adjoint of a linear map, then the adjoint is such that, or the idea is really what needs to be done to make sure that whatever operation, whatever linear map is happening in the second slot is giving us the same scalar or the same inner product that the linear map produced in the first slot. That's how we've defined this adjoint operator, T dagger. If we now talk about self-adjoint operators, now we're saying that the linear map is equal to its adjoint. And in general, T, being a linear map, maps from an input vector space V to an output vector space W. The adjoint now maps from W to V, but if we're forcing T to be the same as its adjoint, that sort of tells us that we have to be mapping from one space into itself, so that the adjoint can map from that vector space back to the original input vector space that was associated with the linear map T. So now we're not saying self-adjoint maps, so keep me honest. We're now talking about self-adjoint operators. And an operator says we're going from one vector space back into itself. And if we wanted to think about the matrix representation of those two maps, then those matrix representations are square matrices, since they're dealing with operators. Now we can sort of continue with our discussion, and now I'll start writing. But suppose I give you this generic linear map, T operating on this 2 vector, xy, and in general we're over the field of complex numbers. So now I'm saying that xy get mapped into the first coordinate being ax plus by, and the second coordinate is cx plus dy. And if that's the case, then what's the matrix representation of that linear map? And that, let's say I call it A. This, I think, is fair game for the exam, isn't it? If I gave you a linear map, I should be able to ask you what is the matrix representation of that linear map. What do we want to fill in? The top row, the first column? What do we want? We want to say our ABCs? Okay, let's say our ABCs. And in what order? Do I read from left to right, or do I read from top to bottom? So now I want A, B in the top row to give me the first coordinate, and then C, D to give me the second coordinate. Now if I'm interested in, and now I'm assuming that I'm working with the standard basis, which those, for this basis, which is really the basis for the input and the output, those are orthonormal if it's the standard basis. And once I have an orthonormal map, then I can create the matrix representation of the adjoint of that linear operator. Meaning, what is now the matrix representation of T dagger if I call it B? Or what do I know this is equal to? It's the conjugate transpose, or the transpose conjugate of the matrix representation of the linear map T. So this, we could say, is now the matrix representation of T complex conjugate transpose. Or that now says that if I transpose. I'm not changing anything on the diagonal, but I need to conjugate it. So I have A star and D star. The off diagonals I need to transpose, so they are going to flip or exchange or move to different locations, but I also need to conjugate those. And that's now my matrix representation of the adjoint. If that's the case, what's the adjoint look like in terms of a linear map? What is the first coordinate in this linear map of my adjoint if this is the matrix representation of that linear map? So now I'm basically saying, oh, we produced this capital A from that T. Now I want you to create from this B the capital T dagger. So this will be A conjugate X plus C conjugate Y. Second coordinate is now B conjugate X plus D conjugate Y. Everybody okay with that? So that's now the adjoint of the original linear map for this operator over a field that's complex. Now if I say, well, what if this linear operator is self-adjoint? So if I now say I want to see what relationships hold for these different coefficients if I want my map T to be self-adjoint. Or that's now saying that I want T to be T dagger. Or if the above linear map or linear operator T is self-adjoint, then in fact the A matrix is equal to the B matrix in our matrix representation of T and our matrix representation of T dagger. Or now I simply have to say, oh, I need to equate or make equal the corresponding elements in this 2 by 2 matrix. Or A is equal to A star, D is equal to D star, or D is equal to its conjugate. B is equal to C star, or C is equal to B star. So let's write that down. Based on A equal B, if I'm wanting a self-adjoint map or operator, I now have been able to conclude that A is equal to A conjugate and D is equal to D conjugate. And what does that imply about A and D, or the diagonal entries in that matrix representation? We know now that if we have a complex number A and a complex number D, and they're equal to their conjugate, then those complex numbers are in fact real. What do we know about the off diagonal? Well, we see that B is equal to C conjugate and C is equal to B conjugate. Those are consistent. And now the off diagonal elements are going to be complex conjugates of each other if our map is self-adjoint. And this actually generalizes to a larger map or operator. So if we have the general form of a self-adjoint operator, now we have this big matrix. Let's say now we want to look at it as the matrix representation of this linear map. We have A11, A22, A33. Let me stop there and say I end up with A sub n. I need my diagonals to be real. My off diagonals, let me say I have A12, A13, here's A23, etc. I can go now to A1 n minus 1 and A1 n. And here I just keep going. This is A2 n minus 1, A2 n. If those are now in place, A sub n minus 1 n, and here is, let's say, A sub what do I know about the elements below the diagonal? Do I know anything about them? They have to be the complex conjugate of all of these that are up above. If I've now labeled these as not being conjugates, I now need this one to be the complex conjugate of A12. I need this one to be the complex conjugate of A13. And I keep going. So that this one is now complex conjugate of A sub 1n, etc. And this is now A sub 2, 3 conjugate. And here is A n minus 1n conjugate. Is that enough entries? And I already said it, but let me just make it clear from the writing with the diagonal entries, the A sub II of S, A sub II's need to be real. And this structure is true for any basis. So this structure or form for the matrix representation of T is true for any basis. And if I have a diagonal matrix which we've referred to as a very nice matrix, haven't we? Because we have a lot of zeros. A diagonal matrix has this structure. Under what condition? Here I'm wanting you to repeat the fact that the diagonals need to be real. If they're complex conjugate, then we don't have that structure. So here a diagonal matrix has this structure if the diagonal elements are real. Now, as I promised as I started today, let's now look at a very simple linear map and see what that sort of allows us to think about when we're talking about numbers, complex and real numbers, versus these linear maps and these adjoints, etc., and self-adjoint maps. So let's examine a simple map hopefully to allow us to gain a little bit more intuition or comfort with this and see how the concepts might generalize. Here we're going to have a simple example showing that the matrix representation of an adjoint is the complex conjugate so I'm giving you the answer in the back of the book. The simple example is showing that the matrix representation of an adjoint is the complex conjugate transpose of the original map, let's say T, or the matrix representation of T dagger is now the complex conjugate transpose of the original map's matrix representation. So here's our example. Suppose that we have this linear map T that maps from C back into C. So this is really more than just a linear map. This is a linear operator, but we now have a linear map from C to shining C. I'm sorry. It just seemed like it needed to be sung. But from C to C. Okay? Or, suppose that I now say that I have T applied to a vector X. And let's just make it as basic as the map is now just going to scale that vector by a complex scalar A. So that A is now an element of our field, and our field is actually the complex number field. And X, we're also allowing that to be in the complex field of numbers. That's our vector. So in this case, A, if we wanted to think about it, is a 1-by-1 matrix that's complex. Which is a complex scalar or a complex 1-by-1 matrix. For this linear map, what's the matrix representation of that linear map T? What's the matrix representation of that linear map? That's just A. So I'm really not doing anything different or making anything. I'm just explaining it maybe in more depth than what you might think about. But now that scalar, think of it like a matrix. And that matrix now is a 1 by 1 matrix. If that's the case, let's now apply this definition of the adjoint and see what happens. Let's apply the definition of the adjoint to see what the matrix representation of the adjoint of this 1 by 1 matrix looks like. Let's now use our definition of an adjoint. And how have we defined the adjoint? How did we create this? It was essentially putting the linear map into another slot, was it not? So it hinges on this inner product. So let's now say that from the definition of the adjoint, we have Tx comma v, and what's the definition of the adjoint allow us to write? What's that equal to? X comma T dagger v. And let's now just assume a particular inner product, and let's assume it's the Euclidean inner product. And that means that we match up components in the two vectors, and the second slot components need to be complex conjugate, or conjugated. So if we do that, what do we have? We now have Tx, that's a vector, and what do we hit that with to form the inner product of Tx and v? Tx really is just a scalar, isn't it? X is a scalar, the linear map was a scalar, so now I need to hit that with the conjugate of the second slot vector, which is v conjugate. And over here, what do I have? If I just sort of follow down what I have on the right hand side, what can I write down? I have x times T dagger v conjugate. Is everybody comfortable with that? All I'm doing is using the inner product, Euclidean inner product, based on this relationship that defines the adjoint of the linear map T. How did we say that linear map was being defined? That was just AX. So now this produces AX. We haven't done anything with this scalar, which is V conjugate. Well, what do we do on the right-hand side? I'll do the hard part. X. Now what? Well, we don't know what it is, but let's just assign it some generic complex variable for now and see what that generic variable needs to equal in order for this equality to hold. Or let's now say that T dagger V is going to be BV complex conjugate, where this B is a yet to be determined scalar. This is, I'll say, an unknown as of now scalar. But we know the linear map is mapping from a scalar to a scalar, and the adjoint maps from where we ended, which was a scalar, back to the input vector space, which is also a scalar. So we know this linear map needs to produce or be represented by a scalar. And I'm just now labeling that as B. But if we push this through a little bit, we have a product of two complex numbers, their conjugate. What does that look like? That's okay, isn't it? And since these are scalars, I can slide them through each other, or this is now B conjugate X V star. And I'm hoping you can now see what I'm wanting to see. I have X V star on both sides, and I have what I need scaling the X V star quantity. Meaning, if I'm trying to find the value, the scalar associated with the adjoint of the original linear map was A, what is B, the adjoint's variable or expression. So now I can see that if these two sides, left and right, have to be equal, hopefully I can see that A must be B star, or B, which is the representation of the adjoint's linear map, is simply the complex conjugate of A star. Or now, if I wanted to write that, I could now say that T dagger V is, I said it was BV, but now I know what B actually is in terms of the original linear map T. That's now A complex conjugate V. Now I know what the matrix representation of that adjoint operator is. It's simply the complex conjugate of the original linear operator's map, which was A. Therefore, the adjoint of a map this was a very basic example, but now I'm wanting us to maybe generalize or think about what that might generalize to be. The adjoint of a map is the generalization of the complex conjugate of a complex number. So now if you're thinking about a linear map being a complex number, the adjoint of that linear map you can think about as being the complex conjugate of the original complex number. And now that might generalize to higher dimensions. Or that if somebody says, oh, I have a linear map and I'm thinking about its adjoint, you can start by just saying, oh, give me a complex number, then the adjoint is like the complex conjugate of that complex number. Staying with this same example, what if I now forced this linear operator to be self-adjoint? What about a self-adjoint operator. If I want my operator to be self-adjoint, I'm saying that I need T to be the same, the linear map to be the same as its adjoint. What does that mean about the complex expressions that we used in this previous example? What were we using for the linear map T? Just A. And what were we using for its adjoint? A star. So now if we're forcing A to be equal to its complex conjugate, what does that imply for this simple one-by-one matrix case? A is real. So now this map is real. So if we want a self-adjoint map, we're really talking about a real number if we're dealing with one-by-one or a map from a one-dimensional space to another one-dimensional space. Meaning, or one way we can now try to summarize this is in the form of a table. Suppose I now say, oh, we can think about numbers. And now I'm actually thinking about the road to reality. That's in your resources. He talks about the development of counting and then going from the counting numbers to the integers and then the real numbers and then the complex numbers, etc. Now we can sort of think that way here by comparing numbers to maps. So here is a number, and in the second column we'll say generalizes to the map. Meaning, if I start with some complex number, let's say it's A1 plus J B1, what does that generalize to if we're talking about a map? What did we start this first one-by-one example assuming? What was A? A is now Z, what I'm calling, so I'm really confusing the notation, but what I had before as A, without a subscript, is really this Z, wasn't it? I said A is a complex number. So this really is just T, our linear map. You give me a complex number, then that's like giving me a linear map. What if I now say, well, what about the complex conjugate of Z? What can I associate or generalize that to look like? Or what do I explain that as? If the linear map was A, what did we conclude the adjoint was? It was its complex conjugate, was it not? So now a complex conjugate of a complex number we could think of like the adjoint map. Where the adjoint map is really defined by TV inner product with W equaling the inner product of V with T dagger W. And one more entry in this table. What if I said the number in the left column was simply real? What if Z was just A1? Or this now is a real number. Then what does that generalize to in terms of a map? A self-adjoint map. So now T would be I guess I better keep my color coding the same. T is a self-adjoint map. Where now we're assuming that TV applied to W is equal to what? What's on the right-hand side if T is a self-adjoint map? So now T is equal to T dagger, so anywhere we used to have a T dagger, well, I'm pointing, now that doesn't make any sense to you, but now we want to replace that. And if T is equal to T dagger, we know how to replace it. We now say that the right-hand side is V, T applied to W. And that now is a way to think about numbers, complex and real, relative to maps. If you get lost, just say, this isn't that hard. He's talking about an adjoint. Oh, well, let me just think about a complex number, then I'm thinking about a complex conjugate. If we're dealing with what? That's a simple map. It's mapping from a scalar into a scalar. That's okay. That's how we start. We start with simple things and we build and make more complex things. So now let's make things a little bit more interesting by stating some corollaries and propositions. Proposition 13 in chapter 7, and it's labeled as eigenvalues of self-adjoint maps are real. So that's the label. Eigenvalues of a self-adjoint map are real. And here's really just the statement of this proposition. Every eigenvalue of a self-adjoint operator is real. We're not going to prove any of the others. Let's prove this one just to kind of warm us up. You'll have to be maybe doing a proof next time that we see each other. So let's see what we can do today. Proof. T is now this linear operator. And what are we assuming? We're assuming that it's self-adjoint. So now we're assuming that T is equal to T dagger. That's the assumption. So now we want to show that if we have an eigenvalue of this linear map, that it's real. Well, if we're talking about eigenvalues, this is important for the exam. This is kind of a review. What's the basic concept if I say eigenvalue and eigenvector that you start thinking? If I say you have an eigenvalue eigenvector problem, what should you be immediately thinking? You're going to start watching TV, aren't you? It's TV is equal to lambda v. So now you have TV is equal to lambda v. That's the relationship where lambda is the eigenvalue and v is the eigenvector. And now we want to put all of those into maybe inner products or something to try to show that lambda must be real when T is equal to T dagger. So the hardest part is knowing where to start. So let's start with that. Let's look at lambda scaling the norm of a generic vector v, but in fact that generic vector is not generic, it's an eigenvector. Yes? How do you know where to start? Well, maybe you don't, and so you know that you need to somehow end up with lambda equal lambda star. And how can we get a lambda star appearing? And we've been playing with inner products. Oh, if I ended up with something in the second slot, a scalar in the second slot, that's going to slide outside the inner product as a conjugate. So I'm kind of hoping to be playing with inner products so that I can get a lambda and a lambda star. And if I'm playing with inner products, oh, that's the norm squared in the Euclidean sense. So that now if I say, well, let's see where this leads, what's another way of writing this lambda times the norm of this eigenvector squared? So this is an eigenvalue eigenvector pair. Now that's just the inner product of v with itself, scaled by the same eigenvalue lambda. Or now I have lambda is v comma v, and this is just from really the definition of the norm. But that I can actually slide that scalar in. What if I put it into the first slot? Now this is exam 2 review, isn't it? Because you need to be able to know these properties of scalars and inner products. If I want to move that scalar inside the inner product, this is now the inner product of lambda v with v. And this is just homogeneity of the first slot. But what is that equal to now? That most recent inner product expression is lambda v, and you said, oh, I'm thinking eigenvalue eigenvector. What's lambda v? That's TV. So now this is really TV inner product with v. This is just the eigenvalue eigenvector equation. And now I know what? Oh, I have an operator in the first slot, and what have I been playing with up to this point? Adjoints. So can I somehow move that operator to the second slot? Sure. By hitting or applying in the second slot the adjoint of t. So that now I have v inner product with t dagger v. And that's just the definition of the adjoint. But what did I assume? I assumed t was self-adjoint, didn't I? So now I can say, oh, this is v, t, v. Well, what's TV? Lambda v. So now I have this. Now I've moved lambda, the eigenvalue, into the second slot. And this is just, again, reusing the eigenvalue eigenvector equation. But now what can I say? Here's where I wanted to somehow show lambda and lambda squared being equal. Lambda squared. Lambda star. I don't even know what I'm looking at. Squares or stars or triangles. I guess I'm eating some kind of cereal, aren't I? Moons, clovers. No, I have nothing yet, but I do have a scalar in the second slot, and I can slide that outside the inner product. And if I do, now I have lambda star inner product with v and v. Or this is really just using the conjugate homogeneity of the second slot. But that now I can write as lambda star the norm of v squared. And that is almost what I started with. I started with lambda norm of v squared. Norm of v squared is a number. I can divide both sides by that same number. And what have I now? So I've now shown so far that lambda norm of v squared is equal to lambda star norm of v squared. And norm of v squared is just a number. I can divide that number out, or divide by both sides by that same number, or now I can say that lambda, for any lambda associated with that linear operator t, has to equal its conjugate. Therefore, that lambda was not specific, it was any lambda. All eigenvalues are real. Now I can draw a square. Right? That doesn't even look like a square, so don't get too critical. That's maybe a rectangle, but it's a square. Questions on that? So now, what did we just learn? What? A lot of stuff. We used a lot of stuff, but it was fairly straightforward, the process. But where did we start? We were saying we want these eigenvalues to be real. How do I show that something that's complex is in fact real? I need lambda to be equal to its complex conjugate. And then I said, oh, how can I get a scalar as a conjugate in the same kind of relationship? I need to be using inner products. And I can use inner products if I talk about the norm of something squared. But what we have learned then is if you give someone a self-adjoint operator, then the eigenvalues of that operator, that self-adjoint operator, are real. And then it's kind of nice, right? Now you can sort of imagine what happens if you get a direction that, and it's in the direction of an eigenvector, you're just getting scaled by that real eigenvalue. It's not complex, it's real. All right, so let's look now at several propositions and corollaries relative to this adjoint and operator, etc. So several propositions and corollaries from the text. And now I'll let you refer to the text for the proofs. We just looked at 7:13. Let's look at 7:14. Here's the label. Over the complex field, TV is orthogonal to V for all V only for what vector is orthogonal to every other vector? 0. So now we need TV to really give us the 0 vector, and the way to get the 0 vector from a map is to have the 0 map. So now over the complex field, TV is orthogonal to V for all V only for the 0 operator. That's the label. And again, 0 is heavily loaded, isn't it? It's overloaded. Here's the statement of proposition 714. If V is a CIPS, what happened to CVS? Now we have a complex inner product space. So that's what SIPs represent, or stands for. So we have now a complex inner product space, and T is a linear operator on that complex inner product space V, such that TV inner product with V is equal to 0 for all V in the vector space V, then T is the zero map. That's all we're saying. That's 714. If we have a map when applied to any vector V in our vector space, and we take the inner product of that TV with V, and it gives us 0 for every vector V, the only map that that's going to work for is the zero map. So the map is such that whatever you apply it to, it gives you the zero vector. So T is equal to 0. That 0, can you see it? There's a map there. That 0 represents a map. 0 represents a lot. This time it's a map. Sometimes it's a vector. All right, that's whatever. Was that a proposition? Or that was proposition 714. Let's look at a corollary 715. And its label is that over the complex field, TV inner product with V is real for all V only for self-adjoint operators. That's the label. So if you have an operator and you apply it to a vector, any vector in your vector space, and then take that vector, the output vector, and inner product with V, if the result is real, then that linear operator is actually self-adjoint. So now if phi is a, you know the drill, if it's a SIPS, complex inner product space, and T is a linear operator on that complex inner product space, then T is self-adjoint if and only if TVV produces a real number, is an element of the reals for all vectors in that complex inner product space, capital V.
So the SIPs include real and complex, or?
Pardon?
The SIPs include like real.
So now SIPS is a complex inner product space, so you could have vectors, let's say in Cn, you could have vectors that are real, but they belong to Cn. Meaning, if this is true for all V, V is complex, and it produces an inner product that's real, then your map is kind of special. Your map is actually self-adjoint. And that actually didn't depend on how we define the inner product, but we're probably dealing with inner products in this case. Most, if I say C to the N, we're thinking Euclidean, but it wouldn't necessarily have to be. As long as what? If I give you an inner product, what does that inner product have to be? That's maybe vague. How do you verify that that is an inner product? It has to satisfy the inner product properties. There's 5 of those. So if I give you an inner product, and now you apply it to this linear map, and you find that no matter what happens, whatever vector you start with, this inner product gives you a real output or a real scalar. Well, that linear operator is self-adjoint, or T is equal to its adjoint. And what did we learn about in the very simple case? What did that linear operator look like if it was self-adjoint? It was real, wasn't it? So Z was equal to A sub 1. All right. So now let's look at something, if getting your head around this. What's another one? Let's go a little bit further. Proposition 16. If T is equal to T dagger and TVV is equal to 0 for all V, then T is the zero map. That's the label. And here is the description. If T is a self-adjoint map or operator in a vector space or on V such that the inner product of TV with V is 0 for all V in vector space V, then T is equal to 0. Didn't we just talk about a linear map being the zero map? What's different between 16 and 14? If V is a complex inner product space and T is a linear operator such that TVV is equal to 0 for all V, then T is the zero map. All right, record that. What's 16? If T is a self-adjoint operator on V. We didn't have to assume that before, did we? Such that TVV is equal to 0 for all V, then T is the zero map. What we're doing here is now proposition 716 extends proposition 714 to real inner product spaces, because we didn't say on a complex inner product space here, did we? We just said V is a vector space. So now we have to, in addition to just having a linear operator, now we need that linear operator to be self-adjoint in order for it to be the zero map. But adds the requirement of a self-adjoint operator. Let me see if I can maybe make sense of that through an example. So what do we... Whoa. No, I don't want to ask you a question, and so I better quit talking. So why do we need T? This linear operator, why do we need T to be self-adjoint? In this last proposition, which was proposition 16, when dealing with RIPS, or real inner product spaces. So let me give us an example. A real non-zero linear map that has TV inner product with V equaling 0 for all V in V. If T was self-adjoint, then the only map T that would satisfy this would be the 0 linear map. Now I'm cooking up a linear map that's non-zero. It's not the 0 map, but you give me a vector V in a vector space V, I can make TV inner product with V equal to 0. So here it is. Let's now specialize this. Let's say that V is R2. And let's say that our linear map T of xy takes x and y, and the first component it creates beta times y, and the second component it's now minus beta times x. What's the matrix representation of T, just so we can maybe be thinking about what's going on? Is it 0 beta and minus beta 0? Is that self-adjoint? It's not, is it? If it was self-adjoint, the matrix representation of this would equal its conjugate transpose. We don't need to worry about the conjugate. Does this matrix equal its transpose? No, we flipped the signs on the off diagonals. And what does this really, if I said what are the eigenvalues of this, again, I'm reviewing for exam number 2. What are the eigenvalues of this matrix? I don't expect you to know this unless you play with matrices a lot, but these are purely imaginary eigenvalues. Plus and minus j beta are the eigenvalues of this matrix. So these are purely imaginary eigenvalues. But what are we really doing here? What do we have going on? If I now look at T, xy, or let me suppose beta was 1. I didn't say what beta was. Beta could be anything as long as it has this structure. But if beta is 1, this is really doing a rotation. So that's how we always get into trouble when we start talking about real, is sometimes when we do rotations in real fields, it messes things up. Essentially, I can make a rotation such that you give me a vector, I can rotate that vector, and now that rotated vector is orthogonal to the vector you gave me to begin with. That's really all I'm doing. So if we do that, here's T applied to xy, inner product with xy. But in this particular case, what is that? T of xy I said was the vector. What did I say it was? It was beta y comma minus beta x. That's the output of T applied to xy. Let me plug that over here. So this is now beta y, and this is minus beta x. That's now in the first slot. And in the second slot, I haven't done anything. But now if I apply the Euclidean inner product to that, what do I have? I have the first components multiplied together added to the second components. Or I now have beta yx, and I'm dealing with real numbers, so I don't need to worry about conjugates, minus beta xy. But what is that? That's equal to 0 no matter what x, y, and beta started out being. So I can give you a non-zero linear map, T, that rotates, and now it can take vectors and give you an inner product of 0. And that map was not self-adjoint. If it was, then that map would have had to be the 0 map. And this is true for all x, y, and beta that are real. So T was not the linear map. Look at that clock for the time. It's very slow, but if you misread your time, you forget that. But that's now where we will stop, and we'll pick up with normal operators after the exam.